Hello, everyone, for this last and evening session. We have three speakers this session. The first speaker is Guillem Domenech. Guillem, would you mind sharing the slides?
I'm on it. Yes, I hope you can see everything.
Yes, we can see the slides. All right. Right.
Okay.
Okay. Yeah, I think we can start the talk right away. So the first talk of the session is by Guillem Domenech, and he'll be talking about gravitational waves from primordial fluctuation. Guillem.
Thank you, Chandra. I'm happy that I can talk about my work in this nice symposium. For this talk, I will focus mainly on the different possibilities behind these gravitational waves from primordial fluctuations. My name is Guillem Domenech. I'm a Fellini Fellow at the ENF in Padova, and I acknowledge support from the European Union with this grant agreement co-fund Marie Curie and ENFN. And well, if you have interest in my work or any questions, you can either check my review paper or send me an email or check my personal webpage. Okay. So let me start. And I'd like to start by putting some context on this title, this gravitational wave from primordial fluctuations. And to do that, I did a drawing for this talk. I hope you can read everything. This is sort of the typical picture of an expanding universe. It starts very small. We don't know how our universe started, but it started very small. And then it expanded. So you have flowing time through the right. And so what I want you to take home from this image is that we have explored some region of the early universe, which is this right-hand side here in green. And in this region, which roughly corresponds to 1 second after the Big Bang, we sort of understand very well the physics, the Big Bang nucleosynthesis, and then there's a moment where the temperature dropped enough down that the photons propagated freely, and this is what we see as the CMB, the cosmic microwave background. And thanks to the observation of these CMB photons and the anisotropy of the CMB, we have very strong evidence of this period of inflation, so exponential expansion in the early universe. But from the CMB, we can only test the first few weefols of inflation. And so there's a big part in the history of the universe which we don't know, which has been unexplored, basically because electromagnetic waves cannot travel freely in this very early universe, and also because small scale fluctuations have been erased by astrophysical processes. So we essentially don't know what happened toward the end of inflation and how we achieved this radiation-dominated stage. But with gravitational waves, there is hope that we can probe this unknown universe. And in this very early universe is when these induced gravitational waves could form, and also primordial black holes. So I will be interested in this region of the history of our universe, okay, which I call the reheating, but can be fairly long. Let me say that these are not the only source of cosmic gravitational waves. I divided here the sources in two. Either they are generated during inflation or from new physics during inflation and after inflation. So during inflation, we could also have primordial tensor fluctuations out of quantum fluctuations. And you could also source directly tensor modes by some gauge fields or axion fields that then become gravitational waves. And after inflation, you can have first order phase transitions, cosmic strings, and maybe parametric resonances in preheating and reheating. So there's a wide variety of sources. And we hope that in the future, we might find some of them, and it might look something like this. So here you can see in the vertical axis the spectral density versus frequency, and different sensitivity curves for detectors, LISA, the SIGO, and LIGO, and some prototype of cosmic gravitational wave spectra. For example, cosmic strings, or first order phase transitions, primordial gravitational waves, and induced gravitational waves. Now, if you want to have an idea of what is the range in the history of the universe that we can probe, you can associate a temperature to the frequency, in the sense that, so this frequency has a mode associated to it, so we can check when this mode entered the horizon and what was the temperature of the universe at that time. And so you find that for 10 to minus 9 hertz, it's around 100 MeV, and for 200 hertz, it's around 10 to the 10 GeV. So this is a huge, many orders of magnitude that we can test this unexplored early universe. And here I wrote some small disclaimer that all these prototype spectra are derived in a radiation-dominated universe. So if at some moment the expansion history deviates from that, the spectrum will change. This is something that I would like to emphasize. Now, okay, the talk will be organized as follows. So first I will briefly review what is the physics behind induced gravitational waves. And I will do it intuitively in the, let's call it standard radiation-dominated cosmology. But then I would like to go beyond that standard cosmology, just by studying what happens if the expansion history is different than radiation domination, and also what happens if we consider different initial conditions. And this talk is based on these papers of mine in the last 2 years. And here I will just show the main results. If you want more details, you can check. So let's start with this brief review. And I would like first to give credit to the first one that noticed, or at least that there's the record that it noticed the effect. And it was Kenji Tomita in 1967, where, in the abstract, he already says that gravitational waves are induced by density perturbations, even if you have no first order metric tensor perturbation to begin with. Then this work was sort of rediscovered by Matarese, and then followed by Ananda and Baumann. And it was not until 2008 that Saito and Yokoyama made the connection between induced gravitational waves and primordial black holes. And then the LIGO detection came, and it was proposed that maybe 100% of dark matter was primordial black holes, or a fraction of it, and it could explain these LIGO events. And then the research on induced gravitational waves exploded. And I describe more detail the history in my review. You can check if you want. And so let's jump into some more rigorous picture of what happens in the early universe. So in the vertical axis, you have the logarithm of the physical scale, and the horizontal axis, you have the scale factor. In green, you have inflation, then radiation domination and matter domination. And the idea is the following. So the first few folds of inflation is when the fluctuations that evolve to the CMB anisotropies are sourced. And we know from Planck that they follow a normal scaling by a spectrum. But then we don't know what happens later, and it may be that there is some multi-field dynamics during inflation, some sudden turns, or maybe an ultra-slow roll phase that enhances the spectrum and gives sort of peak. And then this peak just evolves as usual. It leaves the horizon and freezes, and then it evolves again when it enters the horizon, and the things here, interesting things can happen. So how the generation of these gravitational waves occur? I try to draw some intuitive picture, and just let me focus on a peak spectrum because it's the easiest one. And this means that we have some initial fluctuations on superhorizon scales with a typical, say, wavelength lambda star, and with an amplitude that is drawn from Gaussian statistics. Now it's super horizon, so it doesn't do anything, but there's a moment where the cosmic horizon catches up and the mode has a size, the fluctuation has a size similar to the horizon size. Then it will start to evolve and two things will happen. One is that if the amplitude of the fluctuation, these random fluctuations, is large enough, then it will collapse under its own gravity and will form primordial black holes. And these black holes has a mass proportional to the mass enclosed inside the horizon. So you can relate the mass to the size of the fluctuations. Now, if the fluctuations are not large enough to collapse, they will evolve as usual. They will oscillate. This means they will generate sound waves in the fluid. And all these oscillations will generate oscillations in the metric. And these oscillations will be these induced gravitational waves. And they will have a typical frequency corresponding to the typical scale of the fluctuation. So by this simple picture, you can relate the mass of the black hole with the frequency of the gravitational waves. And I did some diagram to show you the relation between them or the possible relation between them. So on top, you have typical mass ranges for primordial black holes and the gravitational wave window in frequency below. I think the most interesting one now is that maybe the LIGO events, some of them are primordial black holes, which have masses between 10 and 100 solar masses, and maybe could be related to the possible gravitational background detected by pulsar arrays. But I want to emphasize that since we don't know what happens in the early universe, the conclusions can change. For example, with CP, we showed that if instead of radiation domination, you had an early matter dominated phase, you could connect planet mass primordial black holes, which could explain some micro-lensing events seen by Ogle with this gravitational wave background. So it's very important to know what is the impact of the unknown early universe cosmology. So now I will talk in detail about this early universe cosmology and expansion history. So if you have any question on this introduction, let me know now. If not, I will move on. All right. So let me do a quick estimate of the amplitude of these induced gravitational waves. To do that, we need to go to second order in perturbation theory, but it's not too bad. At first order, you have just a free wave propagating. And at second order, you have that the curvature perturbation back reacts onto the metric. Right? So you have now a source which is proportional to the curvature perturbation square. And only with that, we can have an estimate, not too bad estimate, about the amplitude in the peak of these induced gravitational waves. So if you take the spectral density, which is proportional to the power spectrum of H, of the tensor modes, which is H squared, you will have that the amplitude is 5 to the 4th, so the spectrum of the curvature perturbation square, and we have to take into account the redshift factor. You can do that by relating it to the density ratio of radiation today. And putting some numbers, you get 10 to the minus 6 times the power spectrum square in scales much smaller than the CMB. So if you extrapolate the results from Planck, this is almost undetectable. But if you have some enhancement, maybe 10 to the minus 5, 10 to the minus 4, you can detect this signal. And I try to illustrate this here. So you have the spectral density of gravitational waves versus frequency, some power law integrated sensitivity curves. And these dashed lines illustrate the threshold of the amplitude of induced gravitational waves. So if you have 10 to the minus 4 for the primordial spectrum, you will start to see it maybe in pulsar timing arrays and the SIGO. And if you increase it to 10 to the minus 2, then it appears everywhere. Plus, you will have a sizable fraction of primordial black holes. But again, this changes on the expansion history. So let's see what is the main effect. All right, so let me come back to the equations. And let me focus on this part, the second order part. This unknown cosmological phase will have a different expansion history, so the friction will change, but also the evolution of the curvature perturbation will change. So we will have a non-trivial effect on the spectrum of tensor modes in this beyond the standard cosmology. But there's another interesting effect, and is that you have a periodic force to an harmonic oscillator. So when the frequency of the tensor modes is equal to the frequency of this source, there might be some interesting resonances happening. And these resonances will depend on the propagation speed of scalar fluctuations. So I will show you the effect of this beyond standard cosmology with 3 examples. So I will start with a simple one, then I will complicate it a little bit more. The simplest one is a broken power law. So if you have a broken power law for the primordial spectrum, so here you have log of the primordial spectrum versus wave number. This is usually what happens in some single field inflationary models. You have an infrared slope, which is roughly usually less than 4, but in some special cases can be larger than 4. And then you have an ultraviolet tail with a slope, let's call it NUV. In this paper with Vicente, we argued that NUV is related to the local non-Gaussianity, which means that it's related to the second derivative of the inflaton potential. So if we can know about the slope in the UV, we may know about the physics during inflation. Now you consider radiation domination and you compute the induced gravitational wave spectra, and you get another broken power law. So that's why I said this is sort of the simplest case. This broken power law now has an infrared tail, which is universal. It goes as k to the cube. And a UV slope, which now depends on this parameter capital delta, but it's just related to NUV. Okay, so if we find this ultraviolet slope of the induced gravitational wave spectrum, we may go and say something about inflation. But if we now consider that we don't know what happened during the early universe, so we consider a general equation of state, this is what happens. So this broken power law becomes a double broken power law. Now we have an additional scale which corresponds to the scale of reheating. And the slopes, so there's an additional slope, which is 3 minus 2b, and b is this parameter here. And the UV slope also changed with a factor minus 2b. So now only looking at the UV tail, we cannot extract directly the physics from inflation, but we need to see more of the spectrum. So of course, if you see everything, you may disentangle them and say something about FNL or NUV, but no, you need to know what is the expansion history of the universe. So this is the first effect. So you will change the infrared slope with a broken power law, and you also change the UV slope. Now for the second example, let me consider a very sharp peak, so in Dirac delta. And for a Dirac delta, I show you two cases. So these are the induced gravitational wave spectra versus wave number. And if it's a perfect fluid, so the sound speed of the fluctuations is equal to the equation of state, then you see that the spectrum has a resonant peak at this expected frequency or wave number. Now, if the fluid is stiffer, then the resonance gets much sharper and bigger. But instead, if you have a canonical scalar field, there is no resonance at all because it's not kinematic allowed. In the infrared, we will also have this broken power law that I explained before. And this difference in the resonances will be very important for the next case I want to discuss, which is some oscillatory modulations in the spectrum. So if you have some very non-trivial multi-field dynamics, some sharp turns in the inflationary trajectory, you expect order 1 oscillations in your primordial spectrum. Here, let's say it's go like sine of some frequency omega and k. And these oscillations can be imprinted in the induced gravitational wave spectrum that I show here. And this one, I assume that the universe is dominated by radiation. And as you can see, there are also wiggles. And the frequency of these wiggles can be related to the frequency of the primordial features by this equation here. So it depends on the sound speed of fluctuations. This was first studied by these guys in Paris, Jacopo, Sebastian, and Lucas. And they showed that the amplitude in radiation domination cannot go above 20% of this envelope. So the oscillations cannot have more than 20%. But if we include this equation of state as a free parameter, then things are a bit more complicated. You don't know exactly what is the correspondence between the frequency in the oscillations in the induced gravitational wave spectra and the primordial fluctuations. And I would like to show you one interesting example is on a very stiff fluid, or the equation of state is close to 1. Now you can see that the oscillations in the induced gravitational wave spectra are much larger and with higher frequency. And the interesting point here is that if you see the amplitude of these modulations is larger than 20%, say 40% or 30%, this is a clear indication that the universe was not dominated by radiation. So in this way, this would be a clear signal that it was not dominated by radiation. On the other hand, if the sound speed of fluctuations is equal to unity, so it's a canonical scalar field, then you will barely see the oscillations. So I hope I convinced you that the effect of this unknown expansion history is fairly large. Now I think I'm running a little bit out of time, but I would like to also comment on what happens if you change the initial condition. So,
Guillem, you have about 5 minutes.
Yeah. Yes, I think I can glance over this. So usually people consider adiabatic perturbations, just because in the CMB we don't see any isocurvature fluctuations. But on small scales, this doesn't have to be the case. So let me consider what happens if we take isocurvature fluctuations. And to get you some intuition, so I wanted to discuss two models. I'm not sure if I will have time to do that, but anyway, the most interesting one is that if you have primordial black holes in the early universe, this was noted by these people in Paris. These primordial black holes, which are randomly distributed in space, give rise to density fluctuations when you treat them as a perfect fluid. And these fluctuations can be viewed as, say, fluctuations in some cold dark matter fluid. Now, when this would be the initial condition, so the universe is dominated by radiation, but there are some large fluctuations in the primordial black hole distribution or the cold dark matter. Then as time evolves, these fluctuations starts to be converted into adiabatic fluctuations, and then we will start sourcing induced gravitational waves. This mechanism will be relevant for gravitational wave by cold dark matter. And then once the matter dominates the universe, this large isocurvature will be converted into large adiabatic fluctuations, which then induce gravitational waves directly. And the interesting point is that these induced gravitational waves in an early matter era get enhanced if their heating is very sudden. So let me just show you what happens in these two possibilities. So for the gravitational waves by cold dark matter isocurvature, if you have very large isocurvature, you get a detectable signal. And also primordial black holes, you can check this paper by Samuel and Misao. And so the spectrum, here I compare the adiabatic and the isocurvature induced gravitational wave spectra. In red, you have the adiabatic one, in blue, the isocurvature. They are similar, but not quite. So if you see everything, you hope you can distinguish them. And then you can use this spectrum we derive to place some future forecast on the parameter space. And then let me just discuss this last possibility. So if you have these primordial black holes in the early universe, which reheat the universe by Hawking evaporation, this sudden evaporation will create huge velocity fluctuations and a very loud gravitational wave signal. So we use that to put constraints on the initial fraction of primordial black holes, which is this blue line here. And you have a lower bound because you want the primordial black holes to dominate the universe as a function of mass. So this would be the allowed parameter space. And not only this, that if you find a gravitational wave signal, which is very peaked, might be a signal of a primordial black hole reheating. So sorry for going very quickly through these possibilities. Let me go to the summary and then you can ask me questions if you want. I hope I convince you that induced gravitational waves, together with the black hole, primordial black hole counterpart, is a unique probe of the physics of inflation, but we need to know the physics that happen after inflation. Okay, and these physics after inflation, they have clear characteristics, clear signatures, like this IR broken power law or these different resonant peaks. And also, if there is a primordial black hole dominated universe, we can constrain the model. And we can also use these induced gravitational waves to test the initial conditions of fluctuations, either it's isocurvature or adiabatic. And I will stop here. Thank you for your attention.
Thank you, Guillem, for finishing the talk well within the time. We have time for a couple of quick questions, and I see a few raised hands. I'll go from top. Sriram, you have a question?
Maybe you can let Nilanjan ask, and then I will follow.
Okay.
Nilanjan,
Okay.
student, yeah.
Nilanjan,
Hi, am I audible?
please go ahead.
Hello.
Yeah, go
yeah.
ahead, Nilanjan. We can hear you.
Okay, if you just go to the previous slide.
This one?
Yeah, this one. Here, there is a broken power law, and this subdominant where the break is happening. Is there a way to understand at which frequency this break is happening?
This breaking frequency.
Yeah.
Let me remember. Yes, well, some intuitive way to see that. I can explain the peak very well. So
that will come from the cutoff of your isocurvature, right?
Yes, so there's a peak in the primordial spectrum, right? And then yes, okay. So these are so we started with isocurvature fluctuations, right?
Right.
Which have some spectrum, but these fluctuations get a bit, this primordial spectrum gets corrected because once the mode enters the horizon, it decays. So the initial spectrum also gets a broken power law. And so this knee is what you see here. Here.
So you are saying that here you are getting this because primordial black hole is there and the isocurvature perturbation is coming. So
right. So these primordial black holes generate density fluctuations.
Right.
And then these are isocurvature in the beginning in the radiation dominated universe. But then when the primordial black holes dominate, this is converted into adiabatic.
Yeah.
And in this conversion, the spectrum changes a little bit.
Yeah, that way I understand. I mean, there are like two contributions. One is the coming from that psi squared term, and then there is a subdominant contribution.
Right.
And your like that peak part is coming from that psi square part, the resonant contribution, and then from the second term, this contribution is coming. But
all of this comes from the adiabatic, but so.
Okay.
Yeah.
Maybe I'll move to the my second question.
We can discuss later if you want.
Yeah, that will be good actually. I'm a little bit confused as reading the paper. So another question is that when you are talking about an intermediate phase between radiation and inflation.
Yes.
General W domination. You are matching the scalar perturbation in that level, or directly the second one.
Okay, yes. So what I was assuming, I don't know if there's any good figure for that. So I was assuming that right after inflation, we enter this non-radiation dominated universe.
Right.
So the initial conditions from inflation get directly, they give me the initial conditions during this beyond standard cosmology phase. Yeah.
No, what my question was that when the transition is happening from, let's say, one general W domination to radiation domination,
Yes.
we need to match the first order scalar perturbation at that point.
Well, you don't have to dedicate. I mean, so there's some assumptions. The assumption is that the peak is not too broad, so all the relevant modes enter during this non-standard phase. So whatever happens later, it doesn't matter because it's too small or there is no power there. If you have a scale invariant spectrum, then you might have to be careful in the transition, yes.
Yes, particularly even if you have a scale invariant spectrum, then depending on the duration of this intermediate phase, there can be amplification, right? Particularly if
Well, it depends on the width of your spectrum, the width of the peak versus the amplitude, the width of this, the duration of the transition, yes.
No, I'm
But
talking about the scale invariant spectra. If my spectra is scale invariant and
if it's scale invariant and large enough, then you have to take into account everything. So you have to match the first order perturbations and so on.
okay. Now I understand. Thanks.
Thank you. Thank you, Nilanjan, for the question. And thanks, Guillem, for taking those. Raghavendra, if your question is quick, please ask away.
Okay, just a quick question. This is regarding the general picture that you have regarding the second order tensor perturbations, but the sourcing can happen even before the waves, the modes re-enter the horizon, right? Can you comment briefly about the coupling between the secondary tensors and the scalars before re-entry? In general, during. So
during inflation.
Yes, even during inflation, there is still the sourcing can still happen. There are works in this regard, I believe, but can you, I just wanted to know your thoughts.
Yes. So I haven't worked on this option, but if you have some wild dynamics during inflation, you can get large resonances in the induced gravitational waves, yes. But so this happens, I guess, inside the horizon during inflation. So it's an additional piece. So I'm considering what happens after. So in some models, you may have some generation also during inflation. So you will have sort of the sum of both. But I think they do not quite overlap. But this is worth exploring. I'm not 100% sure.
Okay, thanks.
Thanks, Raghavendra. And thanks again, Guillem, for answering all the questions.